What I want to cover today is basically yesterday we started talking about step index logical relations. We added recursive types to the simply typed lambda calculus, and we saw that that led to this sort of circularity, right? When we tried to define the semantics, of recursive types, what values belong to the value interpretation of a recursive type, we ran into this problem that, in the definition, we wanted to use the interpretation of a type that was larger than the type for whose interpretation we were defining. Okay, and we saw how step indexing lets you, basically gives you an induction metric. So that you can define the logical relation by induction on the number of steps and a nested induction on types, if you will. And then we were sort of going through and editing our definitions and talking about it. And so I want to finish doing that. So some of these have the step indices on them, and the ones that we hadn't gotten to, I've left as they were on the board yesterday. Okay? Let me just push the other board up. Okay, I have to do both of them. Okay. So, all right, let's just, so what I want to do today is I want to finish talking about proving type safety for simply typed lambda calculus with recursive types. And then we'll move on to how you use logical relations to prove observational equivalence. Okay, so that's the plan for today. And we'll add polymorphism and existential types and so on to our language and see what happens there. All right. Okay, so just to quickly go through what we had yesterday. So now we have this notion of, we don't just say that, some values belong to some type. We say some values belong to some type for some number of steps k, right? So that's how we're reading our value interpretation of types now. Okay, so true and false belong to the type bool or behave like they have type bool for any number of steps. There's no constraints. We say that a lambda term behaves like it has type tau1 or tau2 for k steps if at some point in the future, when you have j steps left, someone gives you an argument that is going to be well behaved for j steps, gives you an argument that's going to behave like the argument type for j steps, then you can do the beta reduction, plug the argument into the body of the lambda, and that expression should be well behaved for the remaining number of steps, which is now j, right? So j is where you actually do the application. And we were sort of drawing a timeline for this yesterday. Okay. With recursive types, we want to say that a value fold v belongs to, behaves like it has type mu alpha tau for k steps. If for some j strictly less than k, v behaves like it has the unrolled type, the unfolded type tau with mu alpha tau for alpha. All right? So this is where our step index helps. J is strictly less than k, so the definition is well-founded. All right. And then for expressions, we say that an expression E behaves like it has type tau for k steps. And here, we use the k to constrain how long you can run. So if in some j strictly less than k, you get to an irreducible value, then we want to say that that expression behaves like it has type, like a value of type tau for the remaining number of steps. So you've used up j steps here, and now you have k minus j left. All right? Okay, so let's finish editing our definition, so to speak. Let's add some step indices here. I've written the definition of the G relation, right? The interpretation of environment slightly differently today. I find this a little bit easier to sort of parse quickly, so I hope you agree. So I've just split it up into, you define G for the empty environment, and then you define it inductively. So the interpretation of an empty environment is you just have an empty substitution, right? And if we want to say which substitutions belong to gamma with gamma extended with x colon tau, well, we just have a substitution extended with x maps to v, and little gamma satisfies big gamma, and the v that we've just added better behave like it has type tau. Okay, so let's add some k's here. that's easy. All right. Let's add another k here. So that's pretty easy too. We just say that this substitution behaves like this in, gamma with x colon tau. If little gamma satisfies big gamma for k steps, and if the value v behaves like it has type tau for k steps. Right, so that's a pretty straightforward lifting of that notion up. Yes?
So just to make sure I have the English right, that
Yeah.
means each thing in the context we have k steps to differentiate it, not we have k steps to differentiate everything in the context?
Yes, for each thing in the context, each thing that you give me, it better be good for k steps.
Okay.
Not for all of them total. Yes. Okay. So what about our main definition for open terms? So let's just put down how we had this defined yesterday. Yesterday we had this defined as, so this is an open term, so we need a substitution. If you give me a substitution gamma that satisfies big gamma, then I can use that substitution to close off the term, right, gamma e, and that should behave like an expression of type tau. So that's what we had yesterday. Now, where do the k's come in? Everywhere, right, in a sense, right? Okay. So what we want to say is we want this top-level judgment to really mean that E semantically behaves like it has type tau. So what we want to say is that for all k, sorry, I need a bit more room here. For all k greater than or equal to 0, and for all substitutions, little gamma, that satisfy that behave like big gamma for that k step. So first we pick an arbitrary k, right? And a substitution that's good for k steps, a substitution that contains values that are that are all good for k steps. And then we use gamma to close off E, and we say that the closed expression behaves like it has type tau for k steps. Okay, so what happens is you sort of constantly work at some level of approximation, but since you sort of show this or prove this for all k, that tells you that yes, in the limit, E actually behaves like it has type tau. Okay, you want to get that? Okay, so the lemma that we were, so we talked about proving type safety and how it just follows as a corollary of the fundamental property of this logical relation, right? And the fundamental property just says that if E is well typed, then E semantically behaves like it has type tau under gamma, right? That's the thing that we wanted to prove. Okay, so so what I'd like to do next is just go through perhaps one case of that proof, just to give you a flavor of how this works. Actually, no, before I do that, when I stopped yesterday, we were talking about this monotonicity lemma, or this property of types that they have to be downward closed. So the intuition being that if you have a value that behaves like it has type tau for up to k steps, then it better behave like it has type tau for fewer than k steps. Right? That just makes sense given the intuition that we've been using for steps. Okay, so we have this important lemma. We call it monotonicity, or often in papers you'll see it's called types or... Oh, sorry. Thanks. Better? So we want to say the types are downward closed. Okay, so what we want is basically that if you have some V that belongs to tau, for up to k steps, and you have a j less than or equal to k, then v better belong to behave like it has type tau for j steps, right? Okay, there's only one interesting case here. Okay, well, how would we prove this, Lana? By induction on what? Any guesses? On the type tau? Yes, exactly. Okay, so, Say that again? It's just what?
I mean, everything is quantified over 4j instead of k. So obviously
yes, but there's one particular aspect to this that I wanna discuss, which has to do with the definition that we've used for function types. So okay, give me just a second. All right, so we want to prove this by induction on types. Strictly speaking, we really only want to prove this for closed types, right? I mean, we have type variables in our language. We haven't defined an interpretation for type variables, so it wouldn't even mean anything at that point. And I'll come back to that point later today when we add polymorphism and existential types to our language. Yeah, so we just want to prove this for the closed types in our language. So strictly speaking, we should prove it by induction on k and then nested induction on tau. All right? Base case is easy. At 0, every one of these, all three of these, we're going to be able to prove that these sets are downward closed. Let's just look at function types, because this is the part that I want to call your attention to. Here we said that, I just sort of used an intuition. I said, you have a lambda. And what can you do with a lambda? Well, you can apply it either right now or at some point in the future. And I used that sentence, essentially, to justify my use of, for all j strictly less than k here. What if I had not said for all j less than k? What if I had just said, if you give me a v that's good for k steps, and then I do the substitution, and that expression has to be good for k steps? Does anyone want to argue for that definition, or at least wonders what would go wrong if we had done that? Yes? You see it, or is that the nodding? Oh, you want to see where it goes wrong? Okay, all right. So let's imagine. Let's imagine that this isn't here and that this is okay. All right. Okay. This is where it goes wrong. All right. So let's try to prove. Let's assume. So suppose that v belongs to the interpretation of tau 1 over tau 2. All right, that means that v must be a lambda, so let me just actually change it to a lambda right now. Lambda x colon tau 1 dot e. Okay, so what we have to do is we have a j that is less than or equal to k, and we have to show that our lambda term belongs to vj tau 1 arrow tau 2. Okay? All right, so in order to show this, what do we have to do? Well, we have to say, give me a value that's good for now our j steps, right? So we get to say, suppose I have some argument, and it belongs to vj tau 1. Now I'm required to show that e with v for x, it belongs to type tau 2 for j steps. Okay, now, this is the fact we have starting out. Obviously, we're going to have to use it. So let's see if we can use it. Well, in order to use it, that says that if you can give me a value that's good for k steps, then you can conclude something about the expression e with v for x. Now, the only value we have is this v right here, and it's good for j steps. j is less than k. So it's definitely not good for k steps. So we can't use it here. Right? We need to show, we need a value that's good for k steps, but we only have one that's good for fewer steps. You see that? And this has to do with this sort of, the usual thing with functions, this contravariant occurrence. Okay, so if we switch back to our other definition, all right, now let's try to do this. So again, we get to this point in the proof, and now we want to use the fact that we have that our lambda term behaves like it has type tau 1 or tau 2 for k steps. All right, in order to use that, that definition says, give me a value that's good for any j less than k. Okay. Actually, no, I can't say suppose. Sorry. Let's go back and just step through that to do it properly. All right. So this time we have to show that this lambda term is good for j steps. Behaves like it has type tau 1 or tau 2 for j steps. First, we have to say, suppose we have some j prime that's less than j, and suppose that we have a v that behaves like an appropriate argument value for j prime steps. Right? So j prime is less than j, and j is less than or equal to k. With me? Okay. So now we have to show that E with v for x behaves like it has type tau 2 for j prime steps. Just switching things to get to the new, get back to the right definition. Okay. Now, if we want to use this fact, we need to come up with some number smaller than k. Let's use j prime, because j prime is strictly less than j, which is less than or equal to k, right? So j prime is definitely less than k. Okay, so if we instantiate this with j prime here, then we do have a value that's good for j prime steps. So we can satisfy this condition. And therefore, we have that E with v for x is good for j prime steps, which is exactly what we needed to show. Okay? Mysterious board? I need to calibrate. Yes?
In order to we could understand that by under certain cases, when J is equal to K, then by reflexivity, then if J is less than K, then we don't need to add this condition that J is less than K.
We do. Okay, so let's say we do what you're saying, that you're saying that when J is equal to K, we're done by reflexivity. I completely agree. So we only really have to consider the case where J is strictly less than K. But in that case, if you had the definition that I had a moment ago, right, where I didn't have j less than k here, I was just using k here and here, then you still wouldn't be able to prove it. Yes?
So, if we just remove this multiplication like what you said, that's actually the set we are going to have is a set of terms that reduces the value of the basis.
The set of terms. So, by that you mean, yeah, you're trying to sort out what happens in that function space, basically, right? Yeah. That's not quite right what you said, but.
I'm touching a property like that.
Yeah, it's not that. Okay.
One thing that is a bit off-putting is that we use step index to solve foundation problem for the fourth case, and now it's being faithful in the solution case as well. So we didn't have any problem of work.
Yes. So that is definitely true, and that is something that happens with step index problems. Steps sort of, show up everywhere. And there have been in the past few years trying to hide the steps from you so that you don't really have to work with them. But they give you a really, really nice property. Without step indices, the way you would do a logical relation like this for recursive types It's phenomenally hard. You basically would have to set up, like Bob Harper and Lars Berkedal had a paper, and then Bob Harper and Carl Crary had a paper in which they tried to do a logical relation for recursive types. And you basically end up using these ideas from denotational semantics, syntactic minimal invariance, which is a notion that Andy Pitts tried to incorporate from denotational semantics. And you basically set up a logical relation that doesn't have these steps everywhere, right? So when you write it down, it doesn't look obviously well-founded. Now, the first thing you have to do before you can do any of your proofs of fundamental property or whatever is you have to show that such a relation exists. And that's a complicated proof. It's a lot of pages and it's non-trivial. So this, the steps, yeah, they show up everywhere. But the basic machinery is really, really simple. Okay? So yeah, it's, I think it's a better trade-off. Okay? All right. Okay, so I will, so this part is important. Yes?
Yeah, I think this last time, and I forgot the answer. So how come we can't use k-1 there instead of the for all j? Because it seems like we can still prove the
In the definition of fold?
Yes.
Yes, you can absolutely use
Okay.
k-1 here. Because basically what, I haven't gone through the case for recursive types here, but yes, that's where it would come up. You would have to, if you're doing, since we're doing induction on k and then that's induction on tau in order to prove this lemma, things would be fine if you were just, instead of doing this, you were just using this. If you can find that easier, I can use that definition. I guess it is a bit more direct. Yes?
Do these step-indexed logical relations also work to prove normalization?
Also work to prove normalization. There is a paper by Aquinas, Gabor, and Rob Dawkins, I believe, that does that. Uses a nifty little trick to do it. For the longest time, it wasn't really obvious to people how you would do it. It's an interesting paper. It was probably a couple of years ago, 2010.
What type of system do they use?
I think they just have, they probably have recursive types in there. And, since the headline is recursive. Sorry? Oh, no, sorry. It's normalization. No, I can't remember exactly what they use. It can't be, might be. Let me look it up. Sorry, I got two things confused in my head in the middle of answering that question. Of course it's not true. Yes?
What do you exactly mean by like something is good for a k step? Why is it not true that if something is good for k-1 step, then it's also good for k steps?
If something is good for k-1 steps, then it's not good for k steps? Because that would mean, so the whole thing that we're doing, the whole intuition that we're using in defining the interpretation is that this value, any value, behaves like it has type tau for up to k steps. And after k steps, you have no guarantees whatsoever. That's how the whole system is essentially set up. So if you do run for more than k steps, you might actually get stuck. Okay, so we're defining the notion of approximations. We're using the k to define approximation. So basically at step level 0, we start off with a really big set of terms that we think belong to this type or intend to X. All right? And as we take more and more steps, that's the intuition. As you take more and more steps, you cut down that set until, up to the limit, infinity, you eventually have the exact set that you wanted. Okay. So in the limit, only the expressions that actually have that type will be left in the set. Yes?
So will it work if we replace into the definition for k of rule, if we replace ej by ek minus 1?
If we replace in the definition of sorry?
Ek of minus 1.
Okay. If we replace ek with
ej by ek minus 1.
no. Because, again, the intuition is, right, at some point in the future you're given this, and then for however many steps you have left, you have to show that this expression behaves properly. Right, and this is connected to what we were just saying, that we can't use, in this definition, we just have to say, we have to write down the definition so that it says, intuitively, that, the lambda may not be applied right now, it might be applied at some point in the future. And if you try to do something else here, rather than use an arbitrary j that's less than k,
I am averse to that. Actually, it's clear with the definition.
So-
Verifying to what you have.
So basically, you want to say this and leave everything else as it is? No, that doesn't make sense. I'm sure I could give you a counterexample. But identity function, you give it something, right? So let's say you have the identity function, and you apply it to a value, and we know that the value is good for, let's say J is 5 and K is 7. All right, we know that the value is good for 5 steps. You do the application, and now you have to show that the value, which is what you get, right, is good for 7 minus 1, which is 6 steps, whatever, right? So you're stuck. Should the numbers a little further apart, but yeah. Okay. All right. So okay, let's do just one case of this proof. I'm not going to do the trivial sort of thing. Application are pretty interesting for step index logical relations, but we've already covered lambda, yesterday in the simply typed setting, so I don't want to go there again. Let's do unfold. I think it'll just be interesting to see how the proof goes. Okay, so of course it's by induction on this derivation, right? So the case that we're considering is where you have unfold E. It has type tau with mu alpha tau for alpha, and we know that E has type mu alpha tau. Okay, what we have to show is that unfold E semantically behaves like it has type tau with mu alpha tau for alpha. Sorry, it got squished over there. Okay, so we have to show that unfold E behaves like that unfolded type. So let's take a look at what we have to show. Basically, we have to pick an arbitrary k. So suppose we're given an arbitrary k and a substitution that's good for k steps. Then we have to show that if we close off our unfold expression, it behaves like it has the appropriate type. So suppose we have a k and we have a substitution that's good for k steps. We have to show, let me put that here, we have to show that gamma applied to unfold E behaves like it has type tau with mu alpha tau for alpha for k steps. Right? Okay, I'm going to do my usual substitution, push the substitution in thing as a first step, but I'll just erase this and do it right here. Okay, so that's what we have to show. So, if we have to show that something behaves like an expression, like it belongs to this E relation, basically we get to say, suppose that our unfold term steps to something irreducible in j less than k steps. All right, so suppose that j is less than k, and that unfold gamma E in j steps gets to some E prime, which is irreducible. Now we have to show that this expression E prime that we just got belongs to the value interpretation of this type, the unfolded type, tau with mu alpha tau for alpha. And this has to be for k minus j steps. Okay. Any guesses as to what we should do now? So we know that the unfold expression steps to something irreducible, right? So let's examine what happens using our operational semantics. What must have happened? So by the operational semantics, it must be the case that this gamma E must have reduced to something irreducible, right? By the operational semantics, it must be that gamma E in some, let's say, J1 steps, stepped to some E1, and E1 is irreducible. Okay? That's just from the operational semantics, right? Okay, so now, since we're talking about the E term, and E appears up here, right, we can use our induction hypothesis. Okay, so let's use our induction hypothesis. What do we know by our induction hypothesis? That E semantically behaves like it has type mu alpha tau, right? So we know this fact. If we know this fact and we want to use it, what do we have to do? Well, we have to basically instantiate this thing with a k and a substitution, right? We have a substitution that's good for k steps, right? Our little gamma. So let's just pick the same k and the same gamma, the same k that we started out with and the same gamma, all right? And if we do that, instantiate with k and gamma, therefore we get that gamma E behaves like something of type mu alpha tau for k steps. Okay, so this belongs to the E relation for k steps. The E relation says that if you can reduce this to something irreducible, then that thing must be in the value relation, right? So what can we do? So we know gamma E reduces to E1, and which is irreducible. So let's just use that. So we'll instantiate this definition with J1. J1 is, by the way, here J1 has to be less than or equal to J, right? Let me write that down. Okay, so instantiate this with J1. We already know that this expression evaluates something irreducible in J1 steps. All right, therefore, just unfolding this definition, we know that our E1 belongs to V of mu alpha tau for how many steps? K minus J1, exactly. Oh, now it's going to get small. K minus J1. Okay. All right, so we know this. So basically we know that this is a value, right? If we know that E1 belongs to V of mu alpha tau, if we know that something belongs to V of mu alpha tau, we know that that something has to be a fold. Right? Okay, so therefore it must be the case that E1 has the form, let's call it fold V1. All right, and we know that fold V1 belongs to this set. So behaves like it has a recursive type. Okay, so if, out of space now, let's move here. So let's just go back and look at the bits where we were reducing things. So we were reducing something here and here. Basically, this is still what we need to show, right? That this E prime that the unfold expression evaluates to, or steps to, belongs to this unfolded type. Okay, so let's go back, and now we know that the unfold gamma E, it stepped to unfold of unfold E1, right? Because gamma E evaluated to E1, and we know that E1 is actually fold V1. So that must have happened in J1 steps. Now we can take one more step, and we get to V1. The top one is actually in J1 steps, right? Because the top one is just where this expression in J1 steps reduces to this, which is this bit here, gamma E in J1 steps reduces to E1, and later we concluded that the E1 must be a value of the form fold V1. So that's all I'm doing here. Okay? All right. So we know that this unfold expression evaluates to this value in J1 plus 1 steps. So therefore, another thing that we know is that J is equal to J1 plus 1. Just for our sanity, let's write that on the side. Okay, so now what do we have to show? Well, we wanted to show that the expression, the irreducible thing that the unfold term reduces to belongs to that, which is V1, right? E prime is V1. Okay, so therefore, now, to finish our proof, we just need to show that V1 belongs to V of k minus j. I'm just reading off of this line here. Belongs to tau with mu alpha tau for alpha. Okay? All right. How can we show that? What's on the board that might help us in our assumptions over there, or? We have this fact about V1, fold V1, right? E1 is now fold V1. It belongs to mu alpha tau. So we have that fold V1 belongs to mu alpha tau for k minus j1 steps. And we want to show this. Let's go look at the definition of fold, recursive types. Well, that says that for all j less than k, V belongs to this. So do we have a number less than k that we want to use here? Right. So let's just instantiate this definition with k minus j. And this is good because k minus j is strictly less than k minus j1. So we can do that. Therefore, just from the definition, we can conclude that V1 belongs to V of k minus j tau with mu alpha tau for alpha. Which is what we wanted to show. Okay, so that was just to give you a flavor of how this goes. You do some unfolding of definitions, you do some stepping, you examine what happens to the term as it runs. You know, using the operational semantics, you infer certain things. And then you use the induction hypothesis to say something about this term, stepping, etc., right? So that's the sort of flavor that these things have. And you do some step arithmetic along the way. Yes?
From the bottom line on the order there, and finally a little bit fast. So what do we need to know exactly to extract that from the operational semantics?
Okay, so we know here, we know that unfold gamma E. Well, so we're relying on the operational semantics of the determinant.
And all the values.
And all the values, yes.
And values being reduced.
And values being reduced.
Do we need anything more?
I don't think so. So yes, the proofs are tedious to recognize. Okay. Yes.
So this is just an observation, but one reason to maybe use the definition that as you defined it instead of using k minus 1 in the index is there, but it's much easier to use in the proof.
Exactly.
So.
And I was sort of looking ahead and thinking about that. Because otherwise, here we would have now, we would have only known something about this value, this V1 belonging to the set at k j1 minus 1, and then we would have had to do one more step of reasoning and something. Is there another question? No. All right. So I'm going to stop there with type safety. The proofs of lambda and application are interesting, but they essentially follow the rules of the later. Okay. So what I want to do next is start talking observational equivalence, how you prove observational equivalence of programs. And what we're going to do in order to do that is we're going to start changing our logical relation. Right now, we just have this notion of when does a term behave like it has this type, right? A single term. We're going to move to binary logical relations where we talk about two terms belonging to a type, and we'll set up the definitions so that you only say that two terms are related at a type tau if they are in fact, contextually equivalent. Well, I mean, we'll set it up to capture the notion of contextual equivalence. And then we'll show that the logical relation that we set up is in fact equivalent to what contextual equivalence is. Actually, let me back up. I need to define contextual equivalence. So observational equivalence and contextual equivalence, some people use one term, some people use the other. Means the same thing. So the standard definition. So when I say that two programs are equivalent, what do you take that to mean? Okay, and how would I extend this notion to open programs or programs that have free variables? Should produce the same. Okay, so let me write down. So you're thinking in sort of a, you're already ahead in a sense and thinking in a logical relation sort of setting. That related inputs, you get related outputs. Let me write down the completely standard definition of contextual equivalence that has nothing to do with logical relations or whatever method you might use in order to prove equivalence of programs. Okay? So are people, when I say program context, does that, are people familiar with program context? So context is just any expression that has a single hole in it where you can plug another expression. So let's write down, let me back up a bit and talk about program context. So we've defined a notion of evaluation context up there, right? And we've been using it for essentially defining our operational semantics. But in general, let me use the letter C for what we call a general program context. A general program context should be any arbitrary program expression, any E, where you sort of take the E and you leave a single hole in it for where you can plug in another expression, assuming that the expression that you get afterwards is well typed. Okay, so here's the grammar for program contexts for, let's just do simply type lambda calculus for now. So here's a valid program context. Here's another one. Here's another one. Right, so we're just moving the position of the hole in some sense. If E, then E1, else C, right? Let's consider what happens with lambdas. Here's another program context. So you can stick an expression under a lambda. We don't have evaluation context of this form, right? So this is one important way in which general contexts are different from evaluation contexts. Here, with application, okay, you have two positions, and so on. Same idea, fold C, unfold C, and so on. Okay? So that's just the grammar for context. Now, when I say that I want to be able to take an arbitrary program expression and plug it into a context, I have some constraints in mind. In particular, I want to take a program expression of an appropriate type and plug it into a hole of the appropriate type, right? Because not all pluggings of context are going to make sense. They're not all going to be well typed. Okay, so let's define. Push this up. I'm going to write down a context typing judgment. that will have this form. And I'll explain it in a second. Okay? So when we say that a context C has this type, we mean that the whole of the context, this is the type of the whole, and this will be the type of the whole of the entire expression after it has been plugged. So in particular, if you have a context of this type, and you are given an expression of this type, notice that this E has type tau under gamma, right, which matches the type of the whole. So if you're given an expression of this type, then once you plug the expression E into the context C, you will get an expression that has type tau prime under the environment gamma prime. Okay? So that's the way you want to read these typing rules. So I'm not going to show you typing rules for contexts in any detail. There's only a couple that are interesting. How would you write down a typing rule for the most basic context that we have for a whole? So let's say the whole has type this. Same thing? You could do same thing. Generally, it's better to allow, I mean, here you have to say that once you plug something into this hole, you get something of type tau. But in the simply type lambda calculus, we have weakening, right? So if a term type checks, if E type checks under gamma, then E will also type check under any extension of gamma. Right? So we're just going to build that in here. And that's a standard way of doing things. That at the whole, if you have weakening in your system, then you allow it here. Okay?
Are you looking for a syntax heuristic?
Am I looking for?
A syntax heuristic?
Yes. You mean for contextual equivalence?
For typing.
Oh, typing context. Yes, yes. Okay. So in this fashion, we can, this is this is our typing rule for the context, for the most basic context, which is a whole. And we can similarly define typing rules for all of the other contexts that we have in our grammar. Do you want to continue with that? It's really sort of a straightforward exercise. The main thing to remember here is that this is the type of the whole, and this is the type of the expression that you get after plugging in the whole, and it'll type check under this environment. All right? So this is the key bit. Okay? All right. So let's define contextual equivalence. Oh, there's actually, yeah. Okay, so we say that E1 is contextually equivalent to E2 at the type tau if, given an arbitrary program context C, okay, let's pause for a second. Let's do the definition of contextual equivalence for what we have on the board right now, which is simply type lambda calculus with recursive types. So for a language where programs may diverge. All right? Okay. So here we can say if you give me a context. Now, the idea is that I want to be able to plug in these expressions E1 and E2 into the context. So the whole of the context has to match this, right? The gamma tau. And the context has to be such that when you plug in the whole, you get a closed expression, okay, of some arbitrary type. I'll just write tau prime. So let's put a for all tau prime at the front here. So if you give me a context of this type, then if I plug C with E1, that terminates if and only if C with E2 does. Okay? Now, so does this make sense, right? Once we take the E1 or the E2 and we plug it in, this whole expression is going to be a closed expression, C with E1 or E2. It's going to be a closed expression of some type tau prime, but we don't even care exactly what tau prime is. We're just looking for termination. Okay? All right. Now, what if I was working in a terminating language? You would need them to terminate in the same value. So in particular, in a terminating language, you at least need to have a base type which is inhabited by two values, which is good. We have Boolean, right? So there, a standard definition of contextual equivalence would be pick tau prime to actually be bool, and say that CE1, evaluates to V if and only if CE2, well, should never have said, evaluates to V. So they must evaluate to the same value, same Boolean. Okay? All right. Yes?
Quite what we wanted in the language, just things being not terminated. So we have Booleans
Mm-hmm.
and recursive types.
If you have Booleans and recursive types, yes.
Would this still be correct?
This would still be correct. Yes. Except it's sort of unnecessary. You can generalize it.
So I think it depends on some quantifiers that you have with this.
Exactly. Yeah. But this is just so much easier for in a sense when you have termination. Basically, the idea is that you can think of non-termination as, you can always, if two program terms are distinguishable, you can always write down some context where that observes the difference between them and then diverges or not. Right? All right.
How would you define quantities of values as the type of the
Sorry?
How would we define quantities of values in general?
Equality of values in general. So that's the thing. If you want to put values here and talk about equality, then you have to put a base type here. Otherwise, you're sort of back to the problem of well, how do you tell that two functions are equivalent? Right? That's the issue. Okay. All right. So yes.
I was just wondering, so I've been seeing this before. Are these actual rules in the language just used to skirt call by value, or?
To skirt call by value?
Yeah. So call by value would reduce what's going to be applied to a value, and then you're going to reduce. So would this just take a turn and put it in?
So a context, well, I think, so the distinction that you want to keep in mind is the distinction between these general program contexts and evaluation contexts. And you're thinking about evaluation context a little bit, I think, there. Right? Because evaluation contexts define a certain order of evaluation, right? Left to right, call by value. And these contexts are simply, these are simply a formal device for us to say, hey, I have this massive software system, all right? And I want to change just this little component in it. Think of it that way, right? So you have a massive software system. I'm writing down the whole software system, all of your code, except for this tiny little blob, right? That's where my hole is. This whole thing is my context, and this is where there is a hole. So this is just a device for anywhere in this entire program. If I were to take out one little component and replace it with another, assuming that that's well typed as well, right? That swap is well typed, what would happen? So it's nothing about evaluation order and so on. It's just a formal way of specifying what we mean by equivalence.
Okay, so this is meta reading. This is not meta
reading. Yes, exactly. Yeah, I mean, you're thinking, what does this have to do exactly with the definition of the language, right? By definition here, I mean that to mean the stuff that I've been writing on the board in the beginning, right? Here are the terms of the language, the value forms, the evaluation context. Here are the, specifying the operational rules, and then giving the typing rules for the language, right? That basically tells us what the language is, right? So in that sense, it's fair to call general context a form of meta-reasoning because we're trying to formalize what we mean by equivalence. But it's very much connected to the language we are given, right? Because how did I come up with these contexts, which I've erased? I came up with them by examining the grammar for expression, E. Basically, for every expression that I have in my language, and I don't have all of them up there today, I write down a C that corresponds to every single E, right? Except when you have true and false, there's no subterm which you can replace, so to speak, right? So there's nothing to replace there. Does that make sense? Sort of? For now? Okay. All right. Okay, so here's what we want to do. We want to be able to prove that programs are equivalent. And we want to take contextual equivalence or observational equivalence as the formal notion of what we mean by equivalence. So let's see. What I want to do now is, okay, the language that we have right now just has recursive types, right? So here we could do some simple, trivial examples of equivalence. But the more interesting examples of equivalence come up when we start to talk about polymorphism and existential types. So in particular, when you add existential types to your language, you have the ability to define abstract data types. Everyone okay with abstract data types? Right? So like, for instance, a stack is an abstract data type, where you could implement the stack using a linked list or using an array, right? Similarly, there are many abstract data types that we define, and what's interesting is that you write down an interface for an abstract data type, and you could implement it in different ways. So the concrete implementation that, or the concrete data structure that you use to implement it, for instance, may be different in your two implementations. And you'd like to be able to show that if you start out with your stack being implemented using an array, you can later swap that implementation out and replace it with the implementation of the stack that uses a linked list, which is going to be faster or whatever. Similar examples. So you want to know that you can replace one implementation of the interface with another implementation of the interface without affecting the behavior of the rest of the system. That's the basic point. And this is a really important concept, right, for software. It's modularity. It's how we implement large software systems and sort of reason about them in the best case. Okay, so if you could show that you have this implementation, if you could show independently of the rest of your system, independently of what's going on out here, I just want to be able to show that if I had some implementation E1 in here originally, let's say E1 is my stack implemented using an array, and I want to come in and replace that with an E2, I want to know that the behavior of my entire system is not going to be affected. I'm still going to get exactly the same answers, etc. Okay? All right. So that's what the definition of contextual equivalence is buying you. It's saying that if you can show me that E1 is contextually equivalent to E2, then you're good. Okay. But now the problem with this formal standard definition of contextual equivalence is precisely this for all C here, right? This for all C says that regardless of the context that you put E1 or E2 into, regardless of what's out here, in all possible contexts, you can swap E1 with E2. So in order to prove that E1 is equivalent to E2, this definition says, consider all possible contexts. That's not very helpful. Right? That's a tough proof to do, and that's precisely why. So we always take this to be the notion of equivalence that we want, but proving it directly is really difficult, and often, it's not tractable in most cases. Some of it has to do with the fact that one possible context that we're considering is this one, where you have a hole under a lambda and so on, but I won't get into that. So it's because of this quantification over all possible contexts that doing direct proofs of contextual equivalence or observational equivalence is not tractable. So what people do is that they use different proof methods that make it easier to do the proof, so where you don't have this sort of quantification over all possible contexts. So it cuts down the set of cases, these proof methods, they cut down the set of cases that you have to consider in order to show that your E1 and E2 are equivalent. Okay? So you use this alternative proof method to then more easily show that E1 and E2 are equivalent. And what you want from your proof method, whichever one it is that you use, you want that proof method, that definition, to be equivalent to this one. So if you've used that alternative proof method to show that E1 and E2 are equivalent, that should imply contextual equivalence of E1 and E2. Okay? So, in particular, the proof method that we're going to use is logical relation. So we're going to set up a logical relation. So just like we have a definition of contextual equivalence here, we are going to define, I'm going to write E1, and I won't put anything on this, to mean E1 is logically related to E2 at the type tau. Okay? This will be an alternative definition, and our goal is then, it'll be something that makes it easy to do these proofs of equivalence of E1 and E2. And what we want overall is to show that whenever E1 and E2 can be shown to be logically related to each other, then then that means that they are contextually equivalent. That's soundness of the logical relation. The logical relation is sound with respect to our definition of equivalence. So this implies this. And the reverse direction is completeness with respect to contextual equivalence. That would mean that any two programs or program components that are contextually equivalent are in fact logically related. So your proof method sort of handles, in a sense, all possible things. Okay? So we'll get to soundness and completeness later. Right now, maybe best use of my time might be to just formally extend our language with polymorphism and with existential types, right? So that we're set up for next time. Oh, pull down the wrong book. Okay, so we are going to add universal types for all alpha tau and existential types, exists alpha tau. Okay, and I'm going to need to erase some stuff here. Are people familiar with polymorphism for the most part? Show of hands? Okay, good, excellent. All right, then I can do this quickly. All right, so since we have universal types, we want terms that allow us to abstract over type. So big lambda alpha E, right, type abstraction. And we need to be able to take expressions and instantiate them with types. So E applied to tau. Okay? Let's make some up here. Okay, so those are the intro and elim forms for universal types. We also need intro and elim forms for existential types. And we have there a notion of a pack where we pack a value, an expression. So pack tau E as exists alpha tau. And we need an elim form, which I'll put here. We need to be able to unpack values of existential types. So unpack alpha x equals E1 in E2. So if any of you are not familiar with the stuff that I'm putting up on the board, go in and read the relevant chapter of TAPL tonight. Okay? All right. What are the value forms that we want to add? So call by value language, standard thing. Value form for universal types? It's just like lambda, right? So type abstraction. Lambda alpha E value form for existential types? Pack tau v, sorry, as exists alpha tau. I'm going to start writing pack tau v from now on and leave out the exists alpha tau. But yeah. Lambda alpha e. Very good. Thanks for, okay. So lambda alpha e is a value form, right? Because it behaves like a regular lambda, lambda x dot e, in the sense that it suspends the computation that's under the lambda. Okay, so just like the term level lambda suspends this computation under the lambda, the type level lambda suspends this computation under it. So it's a value form. Okay? And then we want evaluation context, so type instantiation for pack. I won't write the as exists alpha tau, and for unpack. Unpack alpha x equals e. Okay. Extend our evaluation rules. Sorry, our reduction rules. So once we have gotten, this, when we're doing type instantiation, once we've reduced this down to a value, it'll have the form lambda alpha e. We instantiate with the type tau, and that steps to e with tau for alpha. For unpack, once we have gotten this down to a value, it'll be something of existential type, so it'll be a pack. So we simply say alpha x equals pack tau v. That'll be the value form for the existential type in E, and that steps to this E with tau substituted for this alpha and V substituted for x. Okay? Now, I'm going to add a new typing environment, delta, which can be empty or have, or contain some type variables that appear free in an expression, and our judgment form changes. So just the standard thing. E now has type tau under a type environment delta that gives us all of the free variables, free type variables that might appear in E or in the type tau, and the value environment gamma, which maps variables now to types which may contain free type variables, but those free type variables have to appear in delta, right? Okay. So delta gamma lambda alpha e has type for all alpha tau if we can extend delta with alpha, and here again comma means disjointness, and under gamma e has type tau. For type instantiation, delta gamma e tau prime, let's say. So if under delta gamma e has a for all type, for all alpha tau, and if we have a type tau prime that is well formed under our environment, in our environment delta, then E applied to tau prime has type tau with tau prime for alpha. Okay, pack tau E as exists alpha tau has type exists alpha tau if what? Let's put the type thing first. Oh, I should use a tau prime here. Okay, if tau prime is well formed under delta, right? And E has what type? E has to have type tau with tau prime for alpha. Right? Sorry. Okay. All right. And finally, unpack. So delta gamma unpack alpha x. So these are E1 and E2 has some type. Let's call it tau prime. Actually, let's call it tau 2. If what? What do we need to know about E1? Yes, it has to have an existential type, so E1 has to have some type exists alpha tau. All right. And now if we want to type check E2, but E2 might have alpha and x free, so we add alpha to the type environment and x colon x colon what? X colon what?
Alpha.
Should x have type alpha? So coming back over here, right? X gets bound to this value v that's sitting inside the pack. The value sitting in the pack has type, this type here, right? But we want to keep the alpha bit of that abstract. So it's just going to be tau, this tau right here. Right? And notice that this is well formed now because even though this type tau has free type variables in it, alpha appears free in it, that alpha appears here. Right? Okay. Is that it? What do we need to know about tau 2? Tau 2 cannot contain alpha, yes? That's a critical bit. So I'll write that simply as, here I'm assuming disjointness, right? So alpha does not appear in delta, so I'll just say tau 2 has to be well formed under delta. But basically, yes, the important bit there is that tau 2 better not contain alpha, so that alpha cannot leak, in a sense. Right? So we unpack this package, this thing that we have of existential type, and we use it in the context of E2. But we don't let the alpha leak, so to speak. Right? The witness type. Okay, so that's just formally how we add polymorphism and existential types. Let's talk about a couple of examples now that we have that. So has anyone heard of free theorems? Theorems are for free. Yes, exactly. Phil Wadler's famous paper, Theorems for Free. So once we have polymorphism in our language, in particular parametric polymorphism, the way we're adding it, we can prove certain interesting things just based on the types. So for instance, the most famous free theorem, perhaps, the canonical one that everyone shows you, is suppose that we have some expression E that has the type for all alpha or alpha, right? The so-called polymorphic identity function. I don't know if everyone is familiar with this. Is everyone familiar with this? Oh, yay. Good. All right. So then I can just state it. So if we know that E has the type for all alpha, alpha, or alpha, and we're given an arbitrary type tau and some value v of type tau, closed value, okay, then we know that E applied to tau v in a language, what happens when this steps? In a language where all programs terminate, we know that this will always reduce in some number of steps to v. Right? The intuition being that this is a polymorphic function. You give it any arbitrary type tau, and then you give it a value of type tau, so the input, the only alpha that it can ever return to you is the input that it got. So evaluating this expression will always give you back the input, right? In a language where, so this is a free theorem, that E must behave like the polymorphic identity function. In a language where programs do not terminate, what sort of free theorem can we get? We can't say that this always reduces to a value V. Right, so either it reduces to a value V or E tau V diverges. I'll write that for diverges, right? It doesn't terminate. Okay, so one of the things that I want to show you is, once we take our unary logical relation and extend it to a binary one, I want to show you how one uses that setup to prove free theorems. The other interesting thing that we'll be able to do is, as I was saying, prove the two implementations of an abstract data type are equivalent. So let's just write a very simple example. Okay, so something with, let me see. So suppose that tau is, here. What do I want to use? Okay. All right? I'm going to write down two expressions, and you tell me if they're equivalent. So E1, I want to write down two expressions of type tau, so two packs, right? All right, so I could create a pack where I use int for alpha, the witness type for alpha, and now I want a pair here. So let me take, since alpha is int, I need to put an integer here, so I'll use 1. And now I need to put a function from int to bool. Okay, so I'll use x int, let's say x equals 0, where equals here means integer equality. Okay, and here's another one. This time I'll use bool as my witness type. Okay, and I'll use true for the alpha here, right, because I need a boolean. And then I need a function from a bool to a bool. In particular, right, let's do not x. Okay, so I have an E1 and an E2. Let's take a look at these. These two expressions are equivalent no matter what context you put them into. Let's see why. Well, okay, what can you do with them? You can unpack them, right, and use them somehow, right? So basically the idea is that we want to treat, under the assumption that int is related to bool, and we want to treat 1 as related to true, like think about it as related inputs to related outputs. This function over here takes inputs of an abstract type alpha, all right? So here, the only alpha that I can give it will be the only alpha that I have, which is this 1. So this function can never be called with anything except for the thing sitting over here, right? So it will always be called with 1. So when we evaluate the function, it'll apply to 1. We'll be checking whether 1 is equal to 0, and we'll get false, right? So if you can ever call this function, if you can ever apply this function to anything, it'll always be this 1, and therefore the function will always return false. All right, let's look at what happens in this situation. Again, it's the same thing. We have a value of type alpha sitting over here. The function wants something of type alpha. So the only thing that we have in our hands, that we can get in our hands, that has, that satisfies the type alpha, is going to be this value true. So the only thing that we can ever apply this function to is true. So when we apply it to true, not of true is going to be false. So when we apply it, we'll always get back false. Right? So if you unpack these packs and you take out the first component and the second component, basically the only interesting thing you can ever do with it is take out the first component and take the second component and apply it to the first. Right? because otherwise you can't use this function in any other way because you can never supply it with an alpha. Nothing else will type check. So basically, these two packages are equivalent, no matter what context you plug them into. Right? And logical relations, the binary logical relations that we want to start setting up, give you a method for proving that. Proving that and for proving free theorems of this form. This is a rather baby trivial example of, two implementations of an ADT. There are many, many more interesting ones, but the point is to show you the techniques to get you to be able to prove equivalence for the really interesting ones. Okay, so we'll start with that tomorrow, all right? We'll extend this to a binary setting.